the screen with all the people in it down here where I can see the people. Oh, give me another moment longer to play little silly computer games over here. You know what? I'm going to have to hide that because I need to see my own stuff. So if anybody has a question or sticks their hand up, Bronwyn's going to have to tell me because I can't see it.
Yes,
all right, let's get cracking.
I will moderate the chat box. Put your questions and comments in the chat box.
Okay, so let's get cracking. I had planned all along, all day long, that I was going to replace that picture of Neptune with a picture of the Earth, and then I realized I never did get around to it. So let me pretend that I intended to do it that way, and I will explain why it's relevant. So we're going to talk about air on Earth. Now, it's not really my subject. My subject is the air of everything else. But the air of everything else is not really all that helpful for us to breathe. And so, for example, when you see this picture of Neptune here, one of the things that we have discovered so far is that there seems to be an inordinate number of planets that are, orbiting other stars that are between the size of the Earth and Neptune. So what are called either sub-Neptunes or super-Earths. They're closer to the size of Neptune, so they tend to be called sub-Neptune. So one of the reasons for why it makes sense to show you an image of Neptune, as if I intended to do it this way, is because this is a more common thing orbiting other stars than us. And of course, when I say us, all I can really mean is things around the size of Earth. What we have not found is anything else that is actually like Earth. And that's really the subject that I'm getting at today. How can we tell if another planet is like us or not? So I should give you a little bit more about me and why I am the person talking to you about that. Let's see here. There we come on. Advance the slide. There we go. So who am I and why do I have something to say about this? I'm Tim Livengood. I'm a planetary scientist. I got my doctorate at Johns Hopkins in Baltimore 31 years ago. And I've been employed by University of Maryland and other people since 1994, but I've been working at Goddard since 1991 with all these other people putting their name on my paycheck. The stuff I actually do is mostly spectroscopy. And if you're not familiar with spectroscopy, that's okay. In a moment, I will show you a graph that will make your eyes whirl around. And in the last couple of years, I've started worrying about the spectroscopy of solid things instead of gases. I've worked with space-based, ground-based observatories, missions, and even instruments orbiting the moon and plans to land instruments on the surface of the moon. I have studied practically everything in the solar system that has an atmosphere, although Uranus didn't work out. And to do that in pictures, these are things I have spent some time studying. The difference between most of these and the ones that you see the big black line around is that those are pictures I'm actually responsible for. An image of the Earth and the moon, which is not a mock-up, that is an actual picture of the moon passing between the spacecraft and the Earth. And the one over on the right is Mars. And you'll notice they're kind of muddy looking compared to a lot of pictures you may have seen. That's because I was doing my best to simulate what the human eye would see. Many of these pictures are put together in ways that you can certainly see a lovely picture, a detailed picture, but they don't really take into account the imperfections of the human eye. And so I was trying to make it look like what we would see. The other thing you probably notice about them is that my pictures are blurry, even though everybody else's pictures are nice and sharp. And all I can tell you is that part is not my fault. When we were planning for the images that you see here from Earth, Moon, and Mars, the guys from Ball Aerospace, who were responsible for building the camera that was on the spacecraft, that took these pictures, they said, well, important lesson learned, never fly a camera that you cannot focus. It was supposed to be in focus, and it didn't work out that way. Now, this is not what I usually do, in a sense. I don't usually do pictures of planets, and in the ones I did do, that was kind of an accident. What I usually do is stuff like this, spectroscopy. And this is what some of my colleagues refer to as a squiggly line plot, the kind of thing we put up, and then people's eyes glaze over and they say, what? And I'm not going to put up many squiggly line plots, but I did want to get across the idea that the great majority of what I do is working with stuff like this, which is giving me details about the composition and the structure of the atmosphere, in this case, Mars. But we have this kind of thing for lots of different planets. They all look different, and they all give you a clear picture of what's in there. And in particular, this picture could only exist because Mars is very rich in carbon dioxide. Now, that's something we actually knew about Mars about 10 years before this instrument was even invented. But this has given us the ability to explore that in far greater detail than anything we've been able to actually fly to Mars, or at least some details we can get from this that are not available in an instrument that's small enough to go on a spacecraft to fly to Mars. They, of course, get other details that we can't possibly see. We use this kind of instrument from here on Earth. Gosh, I meant to make a nicer transition. I feel so bad about my poor PowerPoint skills here today. But this is an observatory in Hawaii that I go to fairly often, called the NASA Infrared Telescope Facility. And when sunset comes and the sky gets dim over the observatory, we go back inside after taking these nice tourist photographs, fire up the old infrared heterodyne spectrometer, and we get to work making our squiggly line graphs of what's going on in the atmosphere of Mars, about half an astronomical unit away. So anyway, enough of the squiggly line plots for now. There's a couple more still coming, but we're going to get back to things that are a little clearer than that. Of course, as I said, I study a lot of things. Here is our sun in light that you and I cannot actually see with our eyes. So, and it's important to understand that's why, even though you can tell, that looks like the sun, there is no telescope you could use on Earth that would show you the sun looking like this, because this was done with a wavelength of ultraviolet light, or actually in this case, extreme ultraviolet light, that doesn't get through the Earth's atmosphere. And over on the right are a bunch of nice visible light pictures of the recognized planets in our solar system, all at their proper size. They're not at their proper placement, because, of course, they're all orbiting the sun. They're all at different places, but they're all in their proper size relative to the sun, to give you an idea of how small or big various things are. And you may be having difficulty figuring out where we are in that. That's us, that little teeny dot there. 70% of what orbits the sun is Jupiter down below that. And if you throw in Jupiter and Saturn, that's 90% of what orbits the sun, including all the comets, all the asteroids, all the other planets. 90% of it is Jupiter and Saturn. We are a teeny weeny little thing compared to all that other stuff. And yet, this is an old plot. I left Pluto in there. You can't see it, but it's in there at the right size. Now, when you look at something like this, you very quickly get the idea that we are insignificant. And by mass, we are insignificant. But mass is not the only thing going on in the world. It's not the only description of significance. Of course, the biggest and most significant thing to us humans living here on Earth is that we live here on Earth, and Earth is a living planet. There is a lot of life going on in this picture. And if you have spotted the caption down in the lower right, you may have realized there's perhaps more life going on in this picture than I realized when I took the picture. At the time, I just thought, oh, look, a lovely beach and people are swimming. And I got all the way down to the beach before I remembered, well, actually, before I saw something that made me aware that, oh, yeah, this is that nude beach in Hawaii that I've read about and did not think I would accidentally find. And standing there wearing long pants and a long sleeved shirt because I was ready to get on the airplane that evening, carrying a camera, felt very embarrassing. I ended up taking a lot of pictures of rocks just so that if anybody walked by, they would feel comfortable that this is a person who has a strange fascination with rocks, but he is not taking inappropriate pictures of people at the beach. Anyway, though, there is, as I said, a lot of life in this picture. And the great majority of it are things like these green leafy things in the foreground. Plants. Plants are critical for our survival here on Earth. They make the air, or rather the portion of the air, the component of the air that you and I breathe that keeps us alive. And of course, we breathe out something, carbon dioxide, that the plants consume. But at some time in the past, we weren't here. The plants were, and plenty of animals were. And then much further back in the past, the animals weren't running around on the surface either, but the plants were here. And then even further back in the past, the plants were not here. And that's the tricky thing. Where did the air come from? The plants need air to survive in. If you put a plant in a vacuum, it dies. So they didn't just make air from scratch. So where did the original air come from on Earth, and what was it made out of? Well, here's an example of one of the ideas for where the air came from. Now, this picture is of rocks that were put on Earth much later than the formation of our atmosphere. These rocks, this is what's called the Deccan Traps in India. It is a huge volcanic province, meaning that it's not like just there's a mountain here, a mountain there. It was a different kind of volcanism here. Lava just came flowing out of the ground and spreading out over an enormous area, covering a lot of ground. And in the process, a lot of gases dissolved in the molten rock came out of it into the atmosphere. It changed the Earth's atmosphere a lot. And for a good long time, a lot of people thought that that may have been what did in the dinosaurs, because this was right around the time that the dinosaurs went extinct. The problem with that theory being that it was not like it was exactly at that time, and it was just one limited region on the Earth, so it was kind of hard to believe that this particular region might have been responsible for actually changing the whole Earth's atmosphere in a way that killed off the dinosaurs. And plus, of course, a lot of other things survived. So it was not a great argument, but certainly it was happening back then. And we think that in the very early time of the Earth, processes like this may have created the Earth's first atmosphere. Rocks, just constant volcanism in the very early formation of the Earth, when it still was very hot from everything smacking together to form a planet, and having gases dissolve out from the rock to form an atmosphere. The question then is what that atmosphere is made out of, and what happened to it. Well, one possibility that people considered for a long time is in the early days of the Earth, there were also a lot more giant impacts on the Earth. Now, this crater I'm showing you, or rather, this is the ancient vestige of a crater at the Manicouagan impact site in Quebec, in Canada. This is actually only a moderate size impact. This is not a giant impact. This is about 100 kilometers across, or about 60 miles. You could drive it in an hour if somebody built a road going all the way across. So it's not that huge as these things go. When we talk about a giant impact, we're talking about something where it may have refashioned the entire surface of the Earth. And so finding things like impact craters from an event like that is just not going to happen. It was so early in the history of the Earth that the surface was already close to the melting point, and then gets hit with a giant impact that remelts the entire surface of the Earth. Now, we do have evidence of a giant impact back then, and that evidence is something that Bronwyn and I were just talking about. It's the moon. The winning theory right now is that the moon actually was formed by an enormous impact of something around the size of Mars, smacking into Earth, being incorporated into Earth, but in the process knocking off an enormous blob of the outer crustal material of the Earth, which formed the moon. This is not guaranteed. It is the best theory we have so far that matches all the evidence we have from rocks on the moon and from rocks on Earth, but we could change our minds if we get new and better evidence. Of course, this is also, what you see here is not the last impact on Earth. 215 million years ago was actually the middle of the first of the three major geologic periods, geologic. I have to get periods, eras, and epochs straight in my head sometime. This would have been in the middle of the Triassic period, when dinosaurs had already evolved. And this is in the middle of it, which means this had nothing to do with wiping out dinosaurs. It certainly was a very bad day for anything nearby, and yet it didn't really change the Earth that much. Whereas another impact, a mere 65 million years ago, that you may be familiar with, did change the Earth a lot. This was at a site that is known today as, well, my best effort at the pronunciation is Chicxulub. And it's a location in the Yucatan Peninsula in Mexico, and it's also about 100 kilometers across. And yet, unlike Manicouagan, this one completely wiped out all of the large dinosaurs. And there's still a lot of debate as to why it made that happen. And so in this process of atmospheres developing on Earth, there is the possibility that there was a first atmosphere before the moon forming impact, or an atmosphere after that, but that was a period when there was still a lot of bombardment of the Earth, which may conceivably have actually removed the Earth's original atmosphere and caused new stuff to form. We've certainly had impacts since then. And then we have what the atmosphere is today, this relatively oxygen-rich atmosphere. And so a lot of what we're going to talk about here is what is the evidence for where our current air came from and what our previous air was like. One of the things we think is that probably the ancient air was a lot like Venus and Mars. So I've made a little bar graph here showing the atmospheres of Venus and Mars. Now, Mars just doesn't have a lot of air. It has very little, but it has air. Venus, on the other hand, has a really extravagant amount of air. In both cases, though, Venus and Mars, the atmosphere is about 95 to a little more than 95% carbon dioxide gas. Whereas on Earth, carbon dioxide gas is just a tiny little bit of the whole atmosphere. That doesn't mean it's insignificant. Again, it's small, but it has a big influence. But our atmosphere is mostly nitrogen. And then the second place gas is oxygen. And then we've got some water dissolved in the air, some argon, and our little bit of carbon dioxide. Now, when I put this plot up here, this is the relative amount of these different things. And so it's not giving us a huge guide as to what we might think our air once was. But if you look at the actual number of molecules in the atmosphere and compare it to Earth, so I'm not giving you a number that says this is how many molecules. I'm saying if Earth is a unit of 1 for the number of molecules, what fraction of that number of molecules does Mars or Venus have? And that's this version. Mars has very, very little of practically anything except carbon dioxide, where Mars actually has 8 times as much carbon dioxide as we do on Earth. So even though it's a very tenuous atmosphere, that's able to be made with 8 times as much CO2 as we have in our atmosphere. Now, Venus has 3 times as much nitrogen as we do, suggesting that Venus lost a lot of that. It still has practically nothing of oxygen, water, or argon, and it has 157,000 times as much carbon dioxide as we do on Earth. So if Earth was born a little more like Venus, I mean, there's still reason to think that Venus has lost a lot of things like the water from its atmosphere, just went off into space. And understanding exactly why one set of things happened to the Earth and the other set of things happened to Venus, that's a hard problem. But there is that question still, if we were like Venus, if we had a lot of carbon dioxide early on, along with other nice gases, where did it all go? And what's the evidence that we once had all of that? And the evidence is in these rocks. It turns out that these rocks are impossible under our current atmosphere. An aphorism I learned recently is the rocks remember. Rocks remember the conditions they were in when the rock formed. These rocks are from, well, you can read it right on there, the Lake Superior Banded Iron Formation. You can see that they're all colored differently because it depends on things like how acidic was the water at the time that they formed. But all of these formed in water, even though it's in, well, it's called Lake Superior, but it's actually, found in the Upper Peninsula of Michigan today, which is why there were iron mines in the Upper Peninsula of Michigan. All of these deposits were at one time, about 2 billion years ago, the bottom of an ocean. And they show that there was iron dissolved throughout that ocean. And it turns out that iron will not dissolve in water that also has oxygen dissolved in it. It had to be under an oxygen-free atmosphere. Now, a very common oxygen-free gas, of course, well, not oxygen-free, it's in the molecule, is carbon dioxide. Now, you still can't argue just based on, well, it wasn't oxygen, therefore carbon dioxide. That doesn't make sense. But carbon dioxide, when it dissolves in water, makes the water acid. And so as part of dissolving all of this iron into the ancient ocean, and acidic water made it easier for it to dissolve in. And these bands that you see in the rocks that are so pretty when you see the rocks today come from periods when there was more and less iron dissolved in the water, with just other sand forming sediment in between, in sediments that formed between 2 and 3 billion years ago. Now, the question then is, okay, so I'm telling you there was carbon dioxide in the atmosphere way back when. Where did it go? Well, it went into rocks also. There's a lot of rocks on Earth that are what are called carbonates, where it is, it's a metal like calcium or other metals, and stuck on the end is a radical called, carbonate, CO3, or yes, carbonate is CO3. So there's a lot of this calcium carbonate, but there are other carbonates all over the Earth, and they form, again, they form in oceans, and they make these deep, deep deposits of ancient carbonate rock. And they form because there was an ocean, and the carbon dioxide dissolved in the ocean, where it was able to react with other things dissolved in the ocean. But it takes time for it to react, which is why, you form these sediments, but they took a long time. Even so, this isn't all of the carbon that was in the atmosphere as carbon dioxide. It's a lot of it, but not all of it. So where did it go? What changed the atmosphere? We know that about between 1.7 and 2.1 billion years ago, the air changed. In what has been called the Great Catastrophe, or the Great Dying. Not catastrophic for us, but catastrophic for whatever was alive on Earth at the time, which for the most part would have been things like this. These are what are called stromatolites, and basically they are rocks made out of snot. Bacteria form mucus that glues together floating mats, or mats of bacteria that are stuck onto things. And these stromatolites form from cyanobacteria. So that's bacteria that photosynthesize. They take in carbon dioxide that's dissolved in the water, and they chemically combine it with water using the energy from sunlight, and they produce oxygen. And so about 1.5 to 2 billion years ago-ish, these things like these stromatolites started to become really common. And they glued themselves to little rocks, and sand would slowly accumulate in all of that mucus, causing new layers of bacteria to grow on top of that sand, forming layers of sand, mucus, sand, mucus, sand, mucus over thousands to millions of years, eventually forming rocks made out of boogers and sand. Now, these days, stromatolites are not common. It was a huge discovery in the 1950s when actual living stromatolites were found at this particular spot in Western Australia, because people had seen stromatolites in rocks as fossils. They gave them a name, that's a stromatolite, but they had no idea where it came from. They had no idea what it did. To actually find things like these weird rocks that when people sawed them open, because you actually can use a rock saw and cut it open and find out that the structure on the inside perfectly matched these fossils that people had not understood what they were looking at. That revolutionized paleontology. And paleontology undergoes revolutions all the time. Sometime in the last 1.5 billion years to today, these things changed the Earth. They produced oxygen. They poisoned the bacteria and bacteria-like organisms that were all over the Earth at that time, and gave rise to things that ultimately look like you and me, and they gave rise to things that look like this. Now, the question is, where did this life arise? I mean, we can see it. We see the fossils. We see what happened. What we don't understand is how life arose. And I'll just answer that big question for you right now. We still don't know. We have ideas, and we're going to talk about some of those ideas. But what actually happened, we don't know. And it's possible that you can't just point to a thing and say, that's what happened. Although it is almost certain that what you see in this picture is not what happened. Charles Darwin had an idea for where life came from on Earth. And given that he was the guy who invented the concept of the origin of species through natural selection, I think we can forgive him for some inaccuracy in some of his early ideas. That is the way science works. We propose an idea, then we go out and test it and find out if it's wrong. We really can't find out if it's right, but we can find out if it's wrong. And so we chip away at our earlier ideas, and then we have to replace them with new and better ideas. Darwin's idea was that life began in his description was always a warm and gentle pond. Now, this particular picture is not actually a warm and gentle pond. It's actually the edge of the ocean, but it looks like a warm and gentle pond. So I'm just trying to be honest with you about it. But we have living things here, living in this gently rolling water at the edge of the rocks. It has everything it needs. It has sunlight. It has chemicals dissolved in the water, dissolved from the rocks. It has air. And that's everything it needs for plants to be alive. And obviously, a reasonable temperature too. And so that was part of why Darwin thought, well, this is such a pleasant and comfortable place, and life, when it first started, surely would have been terribly fragile. But one of the things we've come to realize is that life thrives on adversity. It may be bad for the individual organism, but it's great for the species. And so we started discovering life in very adverse places. And this is an example. This is Grand Prismatic Spring in Yellowstone National Park. And all of those brilliant, funny colors that you see in that, flowing out from that spring, Those are successions of different kinds of bacteria, or actually what are called protista these days. If I'm remembering my biological nomenclature right, I might not be. They are organisms a lot like bacteria, single-celled organisms. There are picky I mean, to me, as a physicist, I would say that's a bacterium. But to a biologist, they would say, oh, how can you say such a thing? But the fact is, they are little single-celled organisms that live in water that is at the boiling point. In fact, the big discovery that I remember reading about in my dad's issue of Science magazine and in Newsweek, it made all the papers, back in the mid-70s, was the discovery that there were these, archaea is also a common word for them, these archaic bacteria, archaea, and their archaic character took a lot of work to conclude. But these things living in the water underneath geysers, where it's held in by the pressure of the rock so that the temperature can actually get above the boiling point. And there are organisms living in that water that is above the boiling point. It may be just an interesting little curiosity that they've been incredibly important in technology since then. Everything done in genetics these days depends on proteins that we have duplicated from those high temperature organisms. It's just one of those little quirks of life. If something invents it, chances are you'll find a way to make it useful. So we had to start thinking, well, maybe life began someplace like this, not in a warm and gentle pond, but in a hot and brutal pond. Something where something that is lifelike gets destroyed, and only the things that are actually able to survive this harsh environment are able to keep going on and copying their molecules and making new things. Another possibility related to that is in places like this. This is in the Atacama Desert in Chile. It's an incredibly dry place. It's chemically hostile in that not only is it dry, but the water that is there is incredibly salty. And that water that is incredibly salty has things living in it. And again, we have to look at it and we say, well, are those organisms that come from things that developed elsewhere and have moved into this hostile environment? Or is this hostile environment the source of living things on Earth, that things had to be capable of surviving a brutal environment in order to carry on with molecules getting together and copying themselves? The molecules that didn't copy themselves just dissolve in the water, but the ones that can copy themselves start making new copies of themselves and take over. And then more complicated things happen, and then you get life. And all I can say, if you're seeing my picture and see me waving my hands a lot, is maybe it's a hand-waving explanation, because we really don't know. It's a possibility, because then yet another thing was discovered in the very late 70s. At the bottom of the ocean, we had our first images of volcanoes at the bottom of the ocean with stuff pouring out of it. And the realization that all those funny looking, funny colored things all around it, some of them are just minerals that have precipitated out of the super hot water when it comes out of this volcanic vent. And then when it cools, those minerals are no longer able to be dissolved and they crystallize. But some of the things you see in this picture, some of the odd structures, are organisms. There are things that are adapted to living in this incredibly weird environment at super high pressure. So again, the temperature of the water can get well above the Earth's surface boiling point. There are what are called tube worms that get their energy from having one end of it stuck almost up to 700 degree Celsius water, and the other end a few meters away in super cold water that's below the freezing point at the Earth's surface. But at this high pressure, the water doesn't freeze at that temperature. And so they get their chemical energy to conduct their life processes from the temperature difference between either end of the thing. And then there are things that live off the tube worms, and there are things that live off the bacteria that are down there. There are bacteria that live off the chemicals that are dissolved in the water. It's just so weird. And for all we know, maybe this is where life arose. Or maybe this is a place where some strange organisms ended up and found that because if they could find a way to survive there, they were safe from predators that had not found a way to survive there. And so they could make a new life. Now, we describe it as if thought is involved, but it's really just a matter of who succeeds and who fails, or what succeeds and what fails. A lot of this question of where did the life on Earth come from, one of the places we're going to look is as far from an Earth environment as you reasonably can get without developing starships, and that's Mars. This is an image from the surface of Mars. Oh, I forgot to save the date on this picture, but this image is from, if I recall correctly, earlier this year or late last year. And part of what is neat about this picture, let me just fiddle with something here. So you should be seeing a little red dot around the screen, is right here in, oh boy, that's hard to see. Right here in the middle of it, you see that little shadow? That is a helicopter flying at Mars called Ingenuity, with the sun behind it, casting its shadow there. There's an interesting little optical phenomenon you may notice, that the sand around it looks brighter than the sand just a few meters away. And the reason is not that the sand is any different. It is an optical phenomenon when you have little grains of material that with the light able to shine straight on it. So it's part of a feature of Mars having very little atmosphere. And so you get this, what's called the opposition phenomenon. When you have the sun right behind you, then the grains of sand are able to reflect light more efficiently back at us. This is just a little thing that happens on all the airless rocky bodies in the solar system. And way over here to the upper left, that is the rover Perseverance, which is on the surface of Mars right now, driving around. This is the only picture we have of a spacecraft or a rover on a planet where it's an actual picture of the whole rover taken from something else. Because this is the only time that we have put two things that are able to move around and both have cameras on a planet at the same time. Well, what Perseverance is doing on Mars right now is looking for signs of ancient life. And the way it does it is it has a drill that's called a coring drill. And so it drills into the surface of Mars in a rock and pulls out a pencil of rock. So the drill bit itself is not like a regular drill bit you buy at the hardware store, where it's just a cylinder of metal that is able to grind its way into the material. It is it's not a rod of metal, it's a cylinder with a hollow core. And so it drills the cylinder into the rock and then breaks it off and pulls it out to give it a core sample, it's called, that goes into the rock, something like, I think they're about 10 or 15 centimeters long. And the idea is to get a look at the interior of the rock, the part that has not been getting weathered by the atmosphere of Mars, the wind, and so on for the past several billion years. We want to see what the rock was like, what its environment was like when the rock formed. Remember, the rocks remember, and so we need to see what they remember. Now, the problem is we don't have instruments on the rover that is capable of examining the interior of that rock. There's just too much for it. And so what it is doing is it is leaving those little sealed pencils of rock in a little sealed canister behind it. And so it has collected 20 some now and has created its first what we're calling a depot on the surface of Mars, where it dropped 10 of these little core samples behind it on the ground. And sometime in the future, meaning we're planning on the order of 6 or 7 years, but what actually happens depends on how quickly we can invent the things we need to invent. Another rover is going to come to Mars, pick up those samples, load them into a small solid fuel rocket, which will be launched from the surface of Mars to Mars orbit, where another spacecraft will fly over and join up with it, all automatically. That requires new inventions. We have never launched a rocket from another planet before. We have never gone and picked up stuff done by another rocket before. We have never had two spacecraft maneuver themselves to dock entirely on their own in the orbit of another planet before. And then the one that picks up the samples off the solid fuel thing is then going to fly back to Earth. And so we've never had a spacecraft leave the orbit of another major planet before. And then finally, when it gets back to Earth, at last we get back to something we have done before, which is to have a sample enter the Earth's atmosphere in an entry shell. But by doing all of that, the reason for going through all of that really painful process is that we can bring the instruments we have here on Earth to examine what's in those rocks in a way that we could not do with the instruments that were able to fly to Mars. Now, this is not the only thing we can do. There have been other attempts to understand where the Earth's atmosphere comes from and how to understand things like, how would you tell that Earth is a living planet? A paper led by Carl Sagan, you may have heard his name, back in the 1980s, 1990s. They used a spacecraft called Galileo to fly by the Earth on its way to Jupiter to say, if we look at Earth as if we don't know anything, would we be able to tell that there is life on Earth? And the answer was, yes, but I would have to say they were cheating, because we understand what life on Earth looks like, and because they were able to fly to a planet where they could get detailed pictures. If we were looking at a planet orbiting another star, we can't get detailed pictures. So we have to figure out, what would you do if all you can do is measure the color of another object? Now, they did a little bit of that, and they found evidence for chlorophyll on Earth, but that's only when you look at the green parts. When you look at the brown parts, the dirt, you really don't see that. So a mission I was involved with years ago, Deep Impact, and I wasn't involved yet. Deep Impact was launched in 2005. Its purpose was to take, let's see, come on, make the little, there it is, this thing, the impactor, to a comet, where it was going to smack it into the comet. They did get their name before the movie Deep Impact started production. They had to sign a memorandum of understanding between the two so that both the movie makers and the space mission could use the name Deep Impact and not argue with each other. So Deep Impact flew to a comet called 9P Tempel 1, and on the 4th of July, because why wouldn't you, the impactor hit 9P Tempel 1, making a big explosion. A lot of stuff came blasting out. The reason was that we wanted to know what goes on under the surface of a comet. And people are still exploiting the data that they got from that observation, including observing the impact from the flyby spacecraft. But afterwards, there was no impactor left, but there was still a flyby spacecraft, a perfectly good spacecraft. What will we do with it? Well, here's what the orbit of that spacecraft did back in 2005. It flew from Earth to Tempel 1. Boom! There was an impact. It then just kept orbiting the sun. And NASA ran a program to say, well, okay, if we were going to do something with it in an extended mission, what would you have? And my group of people, we proposed EPOCh. We're going to use it to study planets orbiting other stars and to look at Earth as a model. In the process, nobody mentioned that it flew right by Mars, as you may have just seen there. And so in early 2008, Deep Impact got back close to Earth, and we started making observations of Earth as a model for extrasolar planets. And then it kept on going. And in 2009, we said, we've realized that there's some other observations we can make. Because the spacecraft is hanging out near Earth, we can look at the North Pole of the Earth. And 6 months later, well, look at this. We can look at the South Pole of the Earth. And hey, let's look at Mars. And then, as it happened, we handed over the spacecraft to the original experiment team, and they flew by another comet called 103P Hartley 2. It's actually not supposed to stop here. Well, I'm going to move on. Okay, so meanwhile, back to the stuff I was working on. We got all these lovely there. Bronwyn, are you there? I hope I'm not talking to empty space.
No, you're still going.
Okay, good. Sometimes that happens, and you realize that you've been hung up for ages. So here are versions of the pictures that we took of Earth on 5 different occasions and of Mars. Now, these are not just, this is not what the pictures look like originally, because we took pictures once every 15 minutes for 24 hours. What I did here was I averaged them all together. So this is what Earth looks like if you had to take a long time to make your observation. So you'll notice it looks a lot more like Jupiter than you might have imagined, like a stripy Easter egg, from the way that all the winds carry things around the Earth and the pattern of clouds as a function of the latitude on the Earth. You'll also notice that Earth gets pretty tiny in some of those pictures. And then at the North and South Pole up pictures, it gets very big again. And then, of course, Mars was tiny. And this is because this spacecraft was designed for observing something when the spacecraft was right next to it with the comet. Using it to look at the Earth was not something we originally intended. So I did want to show you, we also made some movies of Earth from these observations. And so here's an example. The left one is putting together the pictures the way that a human eye more or less would see it. The right-hand one is a picture of what happens if you emphasize where the plants are. And for good, weird technical reasons, plants are red in this picture. And so there's the movie. And we're going along and wait for it. Oh, what happened? There was something it's in the next picture. In this set of pictures, something really interesting happens. Oh, look, there's the moon going right by. And that has turned out to be something we're still examining. If you were looking at an Earth-like planet orbiting another star, what would it look like if it had a moon? And how would it confuse you when you're trying to understand what the air of that planet is like? Because, see, that's the big thing. And that's why I wanted to bring it back to air here. We can't see the rocks on these other planets. If we were looking at a planet orbiting another star, we'll never be able to see the rocks. I mean, maybe someday, a century or so from now, people will be able to build a telescope that can actually see continents on those planets, see oceans, but it's going to be a long time. All of us will be long dead by the time anything like that happens. But that event of 2 billion years ago, when things that photosynthesize replaced the air on Earth, whatever the chemistry of Earth's air was before, they replaced it with air that had very little carbon dioxide and a whole lot of oxygen by comparison. That's the kind of thing we can look for, because that affects the whole planet, not just a little spot here and there. And so here's one of my last couple of squiggly line graphs. This is a squiggly line graph of the spectrum of the Earth in near infrared light, light that you and I cannot see with our eyeballs. And all of those big features where you see a big dip is due to the presence of water in the air. And a little bit of it is due to the presence of carbon dioxide. And there are a few other things like ozone and methane. And so those dips in the air are a hint of what our air is made out of. You'll also see way up there at the left, you see a little one that says O2, the kind of stuff that we care about a lot. That belongs to this little jiggly up and down bit right here. That little dip is oxygen in our atmosphere. The fact is that and the reason you see all this jitter on here, that's not because of the noisiness of the measurement. That's because this is actually 13 different spectra acquired over those 24 hours, just plotted all on top of each other, showing that there's variability in all these things as the Earth rotates. And so that little feature, that little absorption, is the part we care about. And the fact is, it's going to be, at the very least, decades before we will be able to build an instrument that is sensitive enough that it would be able to see a little tiny feature like that, looking at the light from a planet orbiting another star. Where we'll get our chance to learn something will be if you compare Earth to what the same instrument saw. This is from Deep Impact, the same instrument looking at Mars. Those you can see are a lot different. And so looking at Earth, looking at Mars, we can start. I left all the same labels on here, but the details are very different. In particular, even though I told you that Mars has a lot more carbon dioxide than the Earth does, you see that little carbon dioxide feature like that I was pointing out, like the one here and the one here, and even in here, is way weaker. And it's because Mars is also a lot colder than the Earth. There is water in the atmosphere of Mars, but not nearly as much as there is on Earth. And then there's this big carbon dioxide feature over here. And this one is still big because this one is still I'm going to use some technical language here. It is still a well-populated ground state, or lower state at the low temperature of Mars. So this one stays strong even when these ones are weak because of the low temperature. So that's a little bit about how Mars and Venus tell us more about the atmosphere of Earth. Of course, part of the reason that we care so deeply also about all these things is we are discovering now that we are a new catastrophe in the atmosphere of Earth, that humanity has been taking many of those carbon molecules that have been buried in the rocks for hundreds of millions or billions of years, and we've been putting them back into the air where they can change the atmosphere again in a global way. We want to make sure that while we continue sending spacecraft to places like Mars, and I'm showing you, it occurs to me I should have shown you a picture from the surface of Venus, but that wasn't the picture I had handy. Mars is barren. We want to make sure our Earth doesn't get to looking like this. We want it to continue looking like this. So I am going to stop there. Oh, I did add a little bit of text. Oh, no, it disappeared. It was notes to myself. So here we are. This is our Earth. This is the way we like it with the air we have that we like. Okay, so we're going to stop here, and I am going to end my PowerPoint show. Well, and if I haven't driven people away, I'll be happy to take questions.
Well, I see. No, that was great, Tim. Thank you so much.
A stromatolite.
I love the fact. I love that the rocks remember. The rocks remember, and I'm going to remember that.
Just keep in mind, I can't tell you who you're quoting on that, but it isn't me. Well, I mean, you may be quoting me, but I didn't create it. I think Let me just check with the geologist in the room. Hey, dear.
Yes.
How long have people in your subject area, well, your undergrad subject area, been saying things like the rocks remember?
Longer than astronomers.
She says longer than astronomers. She's sure of that.
It was geologists who estimated the age of the universe, or at least the solar system, as being very old before
Yes.
astronomers.
And she makes another good point. Long before astronomers, it was geologists who told us that the Earth had to be old and that the universe had to be old. Now, I'd say we've added to the concept of old considerably, but still.
So Richard, we're opening it up for questions right now. We have a couple of questions. Richard asked, does the moon have any atmosphere at all?
Oh, that is a fraught topic. There is a profound difference of opinion in that there is my opinion and there is everybody else in the astronomy community. I have an opinion based on evidence that the moon has a collisional atmosphere, but only in the morning, the moon's morning, and we just never noticed it. And there are reasons we didn't notice it, and I have reasons for why I'm arguing it, but what we don't have is definitive evidence. That instrument that Bronwyn was mentioning earlier, SSOLVE, is created for the specific and sole purpose of testing the claim. The idea is to land it close to the dawn on the moon, and then as the moon rotates, it would look at the sun and measure the amount of water vapor between the instrument and the sun, and look at how much total there is and how it changes with time of day on the moon. And once we've done SSOLVE on the moon, we'll have the answer. And either the answer will be, I was wrong, and at least I'm the person who shows I was wrong, which is better than having other people show I was wrong, or I was right, and my evidence will be so unassailable that we have an entirely new paradigm. Or, of course, what really happens in science most of the time is somewhere in the middle of that there were things I was right about, but not all of it. And there were things that the other people were right about, but not all of it. So, stay tuned. They have just announced a NASA opportunity to fly instruments like SSOLVE to the surface of the moon. They're looking at, sometime in about the next 4 or 5 years. The thing is, there are a lot of other instruments that also would do important science, and there's only so many you can fly. So I don't know if I will be successful in getting this opportunity, because when there's only a few people who think that something is there, it's a little harder to make the argument that we should measure it anyway. So We'll see.
Well, you'll have to come back and tell us what we find out.
Oh, if the answer is yes, I will be bothering people to say, let me tell you, you need to know.
All right, Jillian asked, will the James Webb telescope be looking at exoplanet atmospheres?
Not only will it be, they already have been. There was a release a couple of weeks ago of JWST spectrum of some dang exoplanet. I don't remember which one. Now, this is not an Earth-like. I'm sorry. This is a sub-Neptune one. So they found, if I recall correctly, carbon dioxide in the atmosphere. And one of the things is you need a James Webb in order to do that, because you can't do it from the surface of the Earth. Our carbon dioxide gets in the way. Well, unless you have an extra special clever instrument like ours. And we don't need to get into the details, but even then, our instrument, although it is able to observe carbon dioxide and other atmospheres from the surface of the Earth, has lousy sensitivity compared to something like the JWST. So you need a high sensitivity thing like that in space so that the Earth's CO2 doesn't get in your way in order to look at these other planets. And the one I'm bringing up in particular, it's like I said, it's a sub-Neptune. They found evidence of carbon dioxide, but they also found evidence, which at this point is iffy, of a molecule called dimethyl sulfide, which is on Earth only made by living organisms. It doesn't just occur naturally on the surface of the Earth. Now, there's a lot of weasel words that go into describing this, because first of all, the evidence in the spectrum isn't real strong, and it's possible that what they're currently describing as possible evidence may in fact be not a sufficiently high quality calibration for the instrument yet. So they're keeping all their weasel words. They are working on it still. It is the danger of doing science by press release. But when you're flying a $10 billion observatory many years late, you do have to do the press releases. People deserve to know that what they've been contributing to is actually producing. So the answer on life in the universe remains maybe. Well, the answer is yes, there is life in the universe, because that's right here. But life elsewhere in the universe remains a big maybe.
And Richard asks, are all the NASA missions tracked from the same place, or are they controlled from different places?
Different places. First of all, the actual tracking is done by what's called the Deep Space Network, which is not quite as awesome as it sounds. It is 3 locations distributed around the Earth of large radio telescopes that we use for communication with spacecraft. So they transmit, they receive. You need the big dish to receive, but you also need it to transmit with enough signal strength that when it gets to the spacecraft, which has by comparison a very small dish, it still can collect enough signal that it's able to receive. Now, we're able to do that on the transmitting end, no problem. On the receiving end, it can get challenging. And as spacecraft get further away, they have to transmit more slowly, because you have to measure the signal for a longer period of time before you could say, yep, that was a 1, or yep, that was a 0. So you have to transmit more slowly when you talk to something like Voyager than what you get when you're talking to spacecraft that are at Mars, that are much closer. Now, as to where they're controlled from, that also, you may even have an individual spacecraft is controlled from more than one location, because there's things like controlling the science instruments, and there's controlling the spacecraft itself. And those may happen at 2 different locations. Deep Impact, that I keep pointing to, was actually controlled from University of Maryland for the science instruments. But for the spacecraft itself, that was controlled from the Jet Propulsion Laboratory in California. At Goddard, they have the control room for the Hubble Space Telescope is at Goddard Space Flight Center. And again, that is the spacecraft control room. The instrument control room is up in Baltimore on San Martin Drive at the Space Telescope Science Institute, right across the street from my alma mater, Johns Hopkins University. I believe they also have the contract for the JWST Science Control Room, but the location of the JWST Engineering Control Room, I'm not actually sure. I don't know if it's at Goddard or it may be at Northrop Grumman's facility up near BWI.
Well, I think that it was fascinating to see how you were able to take the Deep Impact and twist it around and use it to find different data. Was that the first time a space that had happened, or are people doing that more often so that to get more use or different uses out of instruments that are already up there?
Like everything, we get there by baby steps. We have certainly turned spacecraft to purposes they weren't built for, even before Deep Impact. One of the earliest ones, there was a okay, somebody has contributed on Space Telescope having the operations room. There was a spacecraft called IC3, and I can't remember what the acronym was exactly, but the 3 tells you it was part of a group of spacecraft that had been flown, or a series of spacecraft that had been flown. It was for investigating the Earth's plasmasphere, it's called. So plasma that orbits, that is around the Earth, inside the Earth's magnetic field, and measuring Earth's magnetic field. So as a result of what it was for, it did not have cameras, for example. It didn't have spectrometers. But way back in the early 80s, Comet Halley was coming through the inner solar system, or sorry, mid 80s, and a guy named Dave Folta, who I have worked with occasionally at Goddard Space Flight Center, did some calculations and came up with a very, very clever plan that, since IC3 had really kind of used up its lifetime usefulness anyway, they were able to raise its orbit until it got higher and higher orbit, until finally they were able to get it to do a flyby of the moon. And it used the flyby of the moon for a gravity assist to fling it completely away from the Earth-Moon system and throw it out into solar orbit, from which they were able to make, it was actually the first spacecraft to make a flyby of the nucleus of Comet Halley, was an Earth science spacecraft that was sent to Comet Halley because we could. And it had no other real use at the time. So that would be, I think, the earliest example I can think of. Since then, we have done other clever things, like when you've got a spacecraft that isn't doing anything so much anymore, and we'd already had deep impact to show us that running into things is really a good payoff. Well, maybe we should run into things more often. So we have had a few spacecraft that, when they reached end of life, were disposed of by smacking them into the moon. And not just to get rid of the spacecraft so that you no longer have this spacecraft out there that is some kind of navigation hazard, because that's not a realistic hazard for the most part. It was so that you could have other telescopes watching the impact point, so that when it hit, you could see what kinds of things got ejected. Now, so far, measurements from the surface of the Earth have been, haven't paid off very well with that kind of thing. But measurements from other spacecraft orbiting the moon, or orbiting the Earth but in space, like Hubble, looking at the moon, those have paid off. And we've gotten important information about what kind of molecules are stored in the lunar surface in the polar regions. Most importantly being, we thought that it would be maybe some water. And then it turned out that in addition to water, there was also hydrogen gas, carbon monoxide, carbon dioxide, mercury, calcium, and a bunch of other things that were thrown out and vaporized by one of these impacts. That one in particular was designed for an impact, but it's a method that we have been making use of, because it just, I mean, really the instigation was Comet Shoemaker-Levy 9 hitting Jupiter, and it ejected so much stuff up to where we could see it, that was when the comet guys said, hey, what if we do that ourselves on purpose? And, we've been building on this idea.
Tim, Julian asked, what influence does our magnetic field have on the Earth's atmosphere?
Well, there's a few things. I mean, the biggest one is auroras. The Earth, and it goes both ways, because so here's our magnetic field, like a big bubble, protecting the Earth from the solar wind, and also protecting us some from cosmic rays that would otherwise just smack right into the Earth, but instead get kind of deflected. Well, that big bubble is full of plasma, which is ionized gas. It's globally neutral, meaning it has all the right number of ions and electrons to make it electrically neutral, but the electrons are not attached to the ions anymore. They're ions and free electrons. And it has different properties than just a regular gas does. And so our magnetosphere is filled up with this plasma. when there's an event like what's called a coronal mass ejection from the sun, it actually squishes our magnetosphere when that coronal mass ejection comes by Earth a few days later. And when it squishes it, it at that point takes that plasma and now has increased its density because it's filling a smaller volume. And it turns out that it can't maintain that high density. And so what happens is those ions and electrons that are bouncing around on Earth's, they follow Earth's magnetic field. They go into the pole and they make auroras. So it adds a little bit of new energy to the Earth's atmosphere. It makes a pretty glow in the sky. It does some chemistry in the Earth's atmosphere. I don't really know how much. On Jupiter, this is actually a hugely important thing because Jupiter's auroras are about 100 times more energy than what happens at the Earth. But of course, Jupiter is a vast planet by comparison too. Jupiter was my thesis topic, and this was chapter 6. So I kind of remember the answer on that. Actually, it was chapter 4 and 6. But so the so right there, squashing our magnetic field alters the auroras that happen on the Earth. But there's that other bit that I was talking about with galactic cosmic rays. Cosmic rays, even though you say ray, and that sounds like some kind of magic thing, because for a long time we just knew energy was traveling. We didn't know how. So it got this term ray. And then we began to figure out how and realize that some of the things we call cosmic rays are very high energy photons of light. But a lot of the things that we call cosmic rays are very high energy ions, whizzing along at just a hair short of the speed of light. And there's a whole field of astronomy in what accelerates these things to these incredibly high energies. And when they come whizzing through, they hit things in the Earth's atmosphere. And so, for instance, I'm sure everybody here in this crowd has heard of carbon-14 dating. But what almost nobody knows outside the field is where the carbon-14 comes from, because it's not naturally occurring in Earth's atmosphere. Carbon-14 has a half-life of only 5,600 years, or 5,300-ish. I forget the number. I'm confusing a couple of different half-lives in my head. But, between 5,000 and 6,000 years. So it's not here from the formation of the Earth. 5 billion years ago, that's a lot of half-lives. There is no carbon-14 left from the formation of the Earth. So the carbon-14 we have has to be made pretty much now. And what makes it is galactic cosmic rays that make it through the Earth's magnetic field, and they make it through the sun's magnetic field, they make it through the Earth's magnetic field and hit the atmosphere, where they hit the nitrogen-15 in the Earth's atmosphere and transmute it into carbon-14, ejecting a proton in the process. It's a little more complicated than that. But as a result, you get this carbon-14 created in the Earth's atmosphere. So one interesting quirk is that the only planets you have where you can have carbon-14, they have to be nitrogen-rich. Carbon-rich means nothing to them. It has to be nitrogen-rich. So you won't get any carbon-14 in Jupiter, Saturn, Uranus, or Neptune. But you can get it at Venus and at Saturn's moon Titan, because they both have nitrogen-dominated atmospheres, and you get it here. Well, the strength of the sun's magnetic field varies with time, with the solar activity cycle, and that has a huge influence on the cosmic rays that get to us. And the Earth's magnetic field, while it's not varying in strength all that much, although it does some, it varies on a much longer time scale. The sun, varies every 11 years. The Earth, the magnetic field can take between tens of thousands to millions of years to change field strength, depending on what it feels like doing. It is a hard to predict phenomenon, and there are people who are working on that. But as a result, it changes the amount of shielding that the Earth's atmosphere gets, When the magnetic field goes to zero, then the Earth's upper atmosphere gets exposed directly to the solar wind and may start eroding molecules away from the Earth's upper atmosphere, slowly changing the composition of our atmosphere. So our magnetic field protects us from the solar wind, and it provides a part of the protection from the galactic cosmic rays. Again, when in those relatively short periods of a few centuries, when it goes to zero, we get exposed to things we're not used to being exposed to. You get a lot more carbon-14 forming in the atmosphere, and people have seen this in ancient materials. You get, the ozone layer can get altered because these things can destroy the ozone faster than it makes new ozone. It will at least be wild. What it boils down to is the way we live today depends in a very carefully balanced way on the exact way that the Earth's atmosphere is today. It's not that we can't live with things differently. It's that the process of change is always painful. That's evolution. Things change, life either dies or it adapts. And adaptation isn't done by one organism, it's done by the succession of organisms that are better at it. Now, we have culture, and that enables us individually to adapt. But as you may have noticed from looking around, we adapt slowly, at least more slowly than we, by technical standards, have to. Because, we have investments in the way we do things, so it takes time. Sorry, I could go on that subject for a long time.
Well, I think this has been a fascinating discussion tonight and presentation. Thank you so much. And like the stromatolites poisoned our air, we are the modern stromatolites here on Earth.
Yeah. Just remember, it poisoned the previous guy's air.
Right, previous guy's air.
To heck with them. And and by the way, they're still around. They didn't get wiped out. They just got their range very, very shrunk. But you find them in places like geysers and mid-ocean ridges and the chemically weird gunk that forms around the drain in your bathtub. You may have noticed it's orange. That isn't rust. That orange and pink stuff.
Yeah. And there's so much more that we don't know, and we are all striving to learn from each other and learn more about this Earth and our universe. So thank you so much, Tim, for sharing with us tonight. Thank you all for joining us. Stay well, stay curious, stay outside, and when you go outside, take a deep breath and think about our air and our atmosphere.
Treasure it, guys.
Yeah. Take care, everybody. I'll see y'all soon. Join our herd, get into the Mammoth Project, and we'll see you soon. Take care. Bye-bye.
Thank you, everyone. Bye-bye.